Did I hit the record button? Yeah,
Yes.
recording. Okay, so we're very happy to have Felix Leditzky from University of Illinois at Urbana-Champaign, who will give a colloquium today. Felix was born and raised in Austria, and in his hometown is Vienna. And he did his PhD in Cambridge in 2016 with Nilanjana Datta. Then from 2016 to 2019, he was a postdoc at University of Colorado Boulder, joined with NIST. And from 2019 to 2020, he was in University of Waterloo Institute of Quantum Computing and Perimeter Institute of Theoretical Physics. And since 2020, he's an assistant professor in University of Illinois at Urbana-Champaign. And he's expert on quantum information. And he will speak to us about symmetries. I don't remember exactly the title. I don't want to make it up, but symmetries in quantum information theory, something like that. Yes. Thank you, Felix. Thank you.
Thanks a lot, George. Thanks for a nice introduction, and thanks a lot for having me. So, yes, I want to talk a little bit about symmetries in quantum information theory and how we can use them to our advantage in order to describe certain quantum information theoretic processes or protocols. And since this is a mathematics colloquium, I want to introduce all of the necessary quantum language and quantum terminology that we need. And in order to save a little bit of time, I decided to pre-write these intro material, and then later I will write as I go, so that it's a pace that everyone can follow. So let me give you a very short intro on quantum mechanics in finite dimensions, which is the setting for most of my work and for the talk today. So quantum information theory is the study of the manipulation and storage of information that we can encode in quantum systems. And so what is a quantum system? For the non-physicists, you should think of quantum systems as small physical systems that have some number of distinguishable degrees of freedom. And the idea is that we encode our information in these degrees of freedom. Okay, so the best examples are, if you take, for example, an atom, and then the electrons can be in certain states that correspond to the energy level in the atom. And then you might want to encode information in these different energy levels of the atom. Another very important one is when you take a photon, which is a particle that corresponds to the electromagnetic field. And then this electromagnetic field oscillates in a certain direction perpendicular to the direction of motion. And you can, this is the polarization of the photon, and then you can have two basic polarizations called the horizontal and the vertical polarization. And again, you can use these to encode information in this photon system. And another very fundamental example is the spin of particles, and in particular, the spin of electrons, which again, can take two possible states, which are called the spin up and the spin down state. And so the idea is now that we use these systems to encode information, and we want to describe this mathematically. And what we do is that we assign to these quantum systems in our case, finite dimensional Hilbert space, where the dimension of that Hilbert space corresponds to the number of degrees of freedom that we have. So for example, in the polarization of the photon, the local dimension of this Hilbert space would be 2. So this would just be the Hilbert space C2 that we model, that we use to model this quantum system. And now the states of the quantum system are described by so-called density operators. And those are linear operators on this Hilbert space that are positive semi-definite, or just positive. So I hope everybody knows this. I just did this with my linear algebra students 2 weeks ago. So this is a very basic concept. We have an operator where all of these inner products here on the Hilbert space are non-negative. And furthermore, we want the operator to be normalized in the sense that the trace of the operator should be 1. And then it follows from these two properties that the eigenvalues of a density operator form a probability distribution. And this is actually a very nice way of seeing how quantum information generalizes the classical notion of information. And I will come back to this in a second. First, I want to say that while we have this general class of density operators, there's a specific class of density operators, which are the so-called pure states. And those are density operators of rank 1. And so for these rank 1 density operators, you can always find a normalized vector in the Hilbert space such that the state is just given by the projector onto this ray in the Hilbert space spanned by this vector. Okay. So these are the pure states, and a mixed state with rank strictly greater than 1 can always be written as a mixture of pure states. And you should think about this also from a physical point of view, where a pure state corresponds to the preparation of a system in a state that you know, definitely, whereas a mixed state corresponds to a system where you're not sure about the actual preparation of the system. And so then the statistical mixture of these pure states is corresponds to your uncertainty of what state that system actually is in. Okay, let me come back to this idea that the eigenvalues of a density operator are in some way a classical probability distribution. And so this is related to the vector space structure of the Hilbert space, and this gives rise to the so-called superposition principle. So let's say we have a two-level system, for example, a photon with polarization horizontal or vertical. Then what I said before, our modeling Hilbert space will be a two-dimensional complex vector space with an inner product. And then we can choose an orthonormal basis in this vector space where we assign to the two members of the basis the values 0 and 1. And this is really a classical bit that we can encode in this quantum system. So think about a coin that you flip, and 0 corresponds to heads, 1 corresponds to tails. And then we encode these two classical states in our quantum system as these two basis states. But now linearity of quantum mechanics tells us that if we have these two basis states, then any superposition of these two basis states, or mathematically just a linear combination of these basis states, will also be a valid state of our quantum system. So in general, our quantum states, the pure quantum states, will be vectors psi that have some coefficient for the first basis state and some for the second basis state. And we choose those to be such that the state is normalized as required for a quantum state. And so this particular encoding here, where we say the 0 vector here, this E0 is the 0 of our coin, and the E1 is the 1 of our coin. This really is what we call a qubit, which is a quantum encoding or quantum realization of a classical bit. However, as we all know, the choice of basis in a vector space is never unique. And so now the encoding of information also corresponds to that basis choice. So for example, instead of using this the standard basis here, E0, E1, I could also choose a different basis to encode my classical bit. So for example, two very well-known quantum states are the so-called plus and minus state, which are these superpositions of the 0 and 1 state. So I'll call them E plus and E minus in the sequel. And imagine now that we have a quantum coin or some two-level quantum system, a qubit, where we want the probability of the event 0 occurring to be 0.3, for example, and the probability of the event 1 occurring 0.7. Okay, so we have these two probabilities here. And then via the encoding that I showed you before, we would write down the state of this qubit now as this state rho here, where the projector onto this plus state, which we call the 0 state, is 0.3, and the weight on the other projector, E minus, would be 0.7, which would then lead to this diagonal density matrix in this plus minus basis. And then to retrieve these statistics, so kind of like to make a measurement, what value does this quantum coin have? We would then measure this system, which in this simple case is just taking the inner product of our basis states with that density operator. And then this would really, as you can check, give us these two probabilities, 0.3 for 0 and 0.7 for 1. But the point is now I need to know what basis was used to encode the classical bit in order to retrieve these two probabilities. If I, for some reason, thought that the system was prepared not in the plus minus basis, but in the usual standard 0-1 basis, and I perform the same measurement here, I actually get 1/2 out of both measurements. So if I measure in the wrong basis, I have 0 information about the encoding of my classical system in this quantum system. Okay, and then this is reflected that in the fact that when you write out the density matrix in this other basis 0-1, then you have on a diagonal here the 1/2, when this is basically what you measure, and somehow the information is encoded in these off-diagonal elements. And those are not accessible to you when you measure with respect to a certain basis. Okay, so this already now hints at the fact that there's many ways of encoding a classical system in a quantum system. And a fundamental feature of quantum mechanics is that there's no one way to do this. And if you want to retrieve the full statistics of your system, then you need to know the right basis. And I chose this example as a motivation for the topic of my talk, because basically what we're doing here is that we want to determine the eigenvalues of this unknown quantum state, or this unknown quantum coin that someone prepared for us. And so we really want to determine the spectrum of an unknown quantum state here. And this will be the first and main part of my talk, to describe to you how we can solve this so-called spectrum estimation problem by exploiting symmetries in a useful way. Are there any questions so far on this setup? This is a very short intro. There's a lot more to say, and I hope you have questions, but I hope this will suffice for you to follow the rest of the talk. If not, please stop me. So we now want to talk about this task of spectrum estimation. And the first problem that we're faced with is that if we're only given one particle, somehow like one copy of this quantum state, and we don't know in what basis we should measure the eigenvalues, then once we make some choice and measure, we will basically destroy the encoding of the information in the state. Okay, so measuring a quantum state destroys, or maybe a better word is collapses, the information encoded in the state into a certain kind of like subspace of the Hilbert space. Okay, so if we're given a one copy of an unknown quantum state and we're asked determine the spectrum for us, then we will not be able to do this with just one copy, because we might just choose the wrong basis and then it's kind of hopeless. Okay, so it is impossible to determine the spectrum with just one copy of the state. And now what we do in information theory is we go to a setting where, in order to determine the spectrum of this unknown quantum state, we actually get to make measurements on multiple copies of that state that are all identically prepared and independent of each other. Okay, so the setting for us now is that we are given independent and identically distributed copies of the state. And in information theory, this is called IID, which is a very common assumption. So the state rho is this state on the Hilbert space that whose spectrum we want to estimate. And so we're in fact given tensor copies of the state rho. And now we're asked to make measurements on these identical copies of the state. And our task is to estimate the spectrum, make a guess for the spectrum. And we're working this asymptotic setting where we want this guess to be better and better the more copies we have access to. So we want to look at this in the limit of n going to infinity. Okay. So this rho tensor n is now a state that lives on the tensor product of the Hilbert space on which we have that one quantum system. And so the goal is now to measure rho tensor n to obtain a good guess for the spectrum. And again, this should become better and better as n goes to infinity, as we increase the number of copies of the state that we have access to. And I actually, in order to really talk about this in a mathematically elegant way, I want to slightly generalize our notion of measuring a quantum state. So before, measuring amounted to taking a basis and then taking inner products of a pure state with a basis, and those would correspond or would be proportional to the probability of obtaining that certain outcome. And we want to strictly generalize this now. So our more general setting here is that of a so-called POVM, or positive operator valued measure. And those are collections of so-called measurement operators MI. And these MIs are also operators on our Hilbert space. They're all positive semi-definite as well. But now they satisfy this normalization condition where if I sum all of them up, I get the identity operator on the Hilbert space. And so this normalization condition basically refers to the law of total probability. So this means that each I here corresponds to one outcome that I can get in the measurement, and the normalization says that the sum of the probabilities of all of these is 1. Let me write down the formula for the probability. So if we assign a classical random variable to the outcome of that measurement, then the probability of getting the outcome I for that measurement, and here I is this index that we have in the POVM, then this probability is given by the trace of the product of MI with our state rho. Okay, and you see that this is really a generalization of what I wrote down before, because if you choose some orthonormal basis Fi, and you define Mi to be the projectors of these, then the trace of Mi rho is just given by the inner product of Fi and rho acting on Fi. Okay, so this POVM model in terms of these positive operators that sum to 1 is really a generalization of measuring with respect to a specific orthonormal basis. And the task now with spectrum estimation is to find a measurement. Let me again call it MI, with probabilities MI rho tensor n that yields a guess for the spectrum of the density operator. Okay. And the idea is to use, try to use the symmetries that we now have in this problem in order to simplify this measurement and actually make an ansatz for it. Okay, so the idea is to use symmetries. So let's see what kind of symmetries we have in this problem. Okay, so let me write down again this expression for the probability, because this will be the main quantity that we work with. So we have this operator mi, which comes from the PVM, and we measured it. We measure the state rho tensor n. And so it will be useful to think about what kind of symmetries. What kind of symmetries we have for these probabilities. And the first one, that is probably the easier one to describe, is that we have permutation symmetry. Okay, so here the idea is pretty simple. If I have some unknown quantum state rho, and I take n copies of this state rho, then obviously if I permute these states, then nothing happens, right? And what I'm doing here is I let the symmetric group Sn act on this tensor product Hilbert space CD tensor n by permuting tensor factors. So for example, if I have two factors and then the transposition 1, 2 acts on a product state by just swapping them. Yeah, and then you extend this linearly to all vectors in the Hilbert space. And so this is the way the symmetric group acts on the tensor product of Hilbert space of all identical Hilbert spaces. Okay, and so these P operators here are the representation of Sn on the tensor product space. So this is the tensor representation of Sn on this representation space. And now it's pretty easy to see that our state that we're given in order to estimate the spectrum of rho is invariant under the action of all of these permutation operators. Okay, so since I take the same state on every tensor factor here, if I apply an arbitrary permutation of these factors, nothing happens to the state. Okay, so this holds for all permutations in the symmetric group. And so this already kind of tells us that we may want to describe things in terms of irreducible representations of the symmetric group, because we have this invariance property. But we have even more symmetries here, because we also have a symmetry that comes from the unitary group. So we have unitary symmetry. And this stems from the fact that the spectrum of an operator rho and a unitary rotation of that operator rho is the same, right? So it's well known that rho and u rho u star have the same spectrum. When this u is a unitary from the unitary group acting on our Hilbert space CD. And obviously this extends to these probabilities now. So the probability of kind of measuring the spectrum of our state also doesn't care whether we take rho here or any rotated rho, right? So here we have this symmetry here for all u in the unitary group. Yeah, my guess for the spectrum does not depend on the specific rho in this orbit here that I take, so I can impose this symmetry. Yeah? And so this is now what we want to do. So let me now try to impose both of these. Let me maybe, sorry, I should have called these A and B. So let's first look at the permutation symmetry. Then if we insert this invariance property for the state here, so this here is the same as these permutation matrices acting on the state. But by cyclicity of the trace, I can also kind of put this on the measurement operator. Yeah, right. So I can write this as this expression here. And this holds for all permutations in the symmetric group. And now what I can do is I can then replace this measurement operator by the average over that group, just using the discrete measure. And then I get that without loss of generality, I can impose that my measurement operators commute with all of these permutation matrices. Sorry. Right, and so this now imposes, this gives me a lot of structure for these measurement operators, and this also happens for all I. Okay. And on the other hand, if I want to exploit the unitary symmetry, I can basically continue here. So this is in parallel. I can write down what I wrote here. I can again do the same thing where I started with a symmetry for the state, but I can now put this on the measurement operators. So again, using cyclicity. So this here is just the U star tensor n. Like this. And this again holds for all unitaries in the unitary group. And now I can do the same thing. Now this time with the Haar measure, I can actually just average the MIs over the full unitary group in order to make them invariant under each unitary. So as a result, I get that these measurement operators are actually also invariant, or they also commute with all of these tensor unitaries. Okay, so we argued that because of the symmetries that we have for the state and for the problem we try to solve, the spectrum estimation problem, we actually deduce these two commutation relations for the measurement operators of that measurement that we try to find that solves spectrum estimation. Okay, and now obviously the idea is that we try to use these commutation relations as much as possible. And the nice thing is that the two groups that are in the game here and the specific representations of these two groups have a nice relation to each other. And this is the so-called Schur-Weyl duality, which most people probably know. So we have these two representations for the symmetric group and for the unitary group. And they are represented on this common representation space, which is the tensor product of our fixed Hilbert space on which the quantum state lives. And so now Schur-Weyl duality, actually, sorry, let me just copy this to the next page. So that I don't need to copy this once more. So we have these two representations on the representation space CD tensor n. And now Schur-Weyl duality tells us that these representations span each other's commutants. And so there's a nice decomposition of this representation space into the irreducible representations of these two groups. And they're nicely paired with each other. So what we can do is we can decompose the representation space into a direct sum that runs over Young diagrams. I will say in a minute a little bit more. And then here we have these two representation modules. Let me call them V lambda D and W lambda. And so what do we have here? Well, first of all, these lambda Ds are Young diagrams. Of n boxes. And the subscript D here means that it's at most D rows. Or D rows if we just fill them with zeros if they're empty. And we know that the Young diagrams correspond to partitions of the integer n. So this means that the lambda will be a collection of integers lambda 1 to lambda d. We order them they're all non-zero. Sorry, they're all non-negative, and their sum is equal to n. So that's what I meant by the n boxes. Okay, so the Young diagram is just a graphical kind of realization of these partitions. Okay, and what are these two spaces or modules that appear in the Schur-Weyl decomposition? So the V lambda D is a so-called Weyl module, which corresponds to an irrep of the unitary group, and the W lambda is a so-called Specht module, which is an irrep of the symmetric group. And the nice thing is that the unitary group only acts on these factors and acts as the identity on these, and the symmetric group only acts on these factors non-trivially, and it acts as the identity on these. So this is the statement that these spaces are each other's multiplicity spaces. Since this is fairly well-known facts from representation theory, I will not say more about this. I hope this is fine. So I just kind of want to use this now. And we use this in the fact that since these measurement operators are they commute with these with all permutation operators and all unitaries represented in this diagonal way. This holds for all u in UD. Then by Schur's lemma, we can deduce that these measurement operators, if we impose these symmetries, have a nice form, a nice diagonal form with respect to this Schur-Weyl decomposition. So this is kind of the crucial mathematical point now, that we apply Schur's lemma to this. And because of the commutation relations here, we get that these MIs are diagonal in these with respect to this decomposition. And so another way of saying this is that the MIs okay, so let me just write, they respect the Schur-Weyl decomposition. This is maybe a weird way of saying it. What I mean to say is that they're diagonal with it, with respect to it. Or block diagonal. Let me say block diagonal. And so since the MIs are supposed to give us an estimate of the spectrum, it's now, in a way that I presented it, it's kind of like clear that the spectrum should have something to do with these Young diagrams. And this was the big insight for the people who figured this out. So the crucial idea now for spectrum estimation is that we try to measure these summands in the direct sum decomposition, and then we use basically the Young diagram that we get as an ansatz for the spectrum. So what we do is, because of this formula here, if we divide by n, then we get a valid spectrum for a density operator, because this is now a probability distribution. So we use 1 over n times lambda as a guess for the spectrum of rho. Or in a little more detail, we let, maybe let me use a different letter. Let me denote the orthogonal projection onto these summands in the Schur-Weyl decomposition by pi lambda. So the pi lambda just projects onto these summands here. So let pi lambda be the let's say just the projection onto the lambda summand in the Schur-Weyl decomposition. Then obviously these projections are positive semi-definite operators, and because they're projections onto these summands in the direct sum decomposition, their sum is 1, right? So if I sum over all lambda Young diagrams of n boxes on at most d rows, then I just get the identity on my Hilbert space. And so that means that this collection of projections is a valid P of n. Okay, so we may use it in order to try to estimate the spectrum. And we do this, and now the probability of obtaining the answer lambda bar for estimating the spectrum is now given by the trace of these projectors times the IID copies of my state. Okay. And what you let me again copy this to the next page. What you can do now using what you can do now using tools from representation theory is that you can really compute what happens to these probabilities in the limit. And so what you do now is you use Schur-Weyl duality and information about the irreps to prove that this guess of the spectrum converges to the true spectrum of the density operator in distribution as n goes to infinity. Okay. So here we view this as a random variable. Okay. And the law of the random variable is given by this. And so we have now used the symmetries that are kind of built into the task of estimating the spectrum of an unknown quantum state in order to deduce a protocol that becomes perfect asymptotically as we increase the number of copies. This is not to say that if we have only finite, if we only have access to a finite number of copies, that this is the best thing to do. Okay, so this is just one way to do it that asymptotically gives us the right answer. And it has a certain mathematical appeal because we can use the structure from Schur-Weyl duality and from the irreps to compute these probabilities here. Okay. Okay, so this is spectrum estimation. And now in the last part of the talk, I want to explain how we can use similar ideas in a quite different information-theoretic protocol that's based on teleportation. Okay, so this is now the section on entanglement and teleportation. So when we have quantum systems that consist of of subsystems, and in the same way as we just did. Okay, so we had a state rho, but we actually took copies of it, and we had this big Hilbert space that described the whole system consisting of these individual, you could call them particles. Okay, and so now we want to ask, what are the possible correlations that we can have among these so-called multipartite quantum systems? So we let again CD describe a D-level quantum system. This is often called a Q-dit, and Q-bit is the 2-level version of this. And assume that we have a bipartite quantum system. What are the possible correlations? The easiest case is if we have no correlations at all. So if we have uncorrelated states, this corresponds mathematically to product states. So the thing that we were given in the spectrum estimation problem was an example of that. So here we have just rho 1 tensor rho 2, product states where each of these states is just some state on this single quantum system. Okay, so this is not a very exciting situation. A more exciting situation is if we have so-called classical correlations between these two systems. And these are basically convex mixtures of product states. So here we, let me write it in a slightly different form now. So I take some probability distribution pi, and some product states rho I and sigma I. These are all just states on our Hilbert space. And so there is some correlation in these states, because basically that label I, if I can somehow measure that, then I have some kind of like classical information about this system. Okay, I don't have any quantum correlation because all of these states are still products. Okay, so these are the so-called separable states. Yeah, every bipartite state that I can write in this form is a separable state, and this is you can also just define it a little more like a little quicker as the convex hull of the product states. Okay, but still, even though these states are now correlated, this is not a genuinely quantum correlation. And the quantum correlations are now everything that cannot be written as a separable state. Okay, so the quantum correlations is now everything that is not separable. And those are the so-called entangled states. So this is a very, very short and rough intro. There's a lot more to say about correlations. This is a very active field of research, but this is kind of the general idea of like different classes of correlations that we can realize on quantum systems. Okay. Let me give you an example for these entangled states, and this will be a very important one that we also use later. The so-called maximally entangled states, which I can describe by these vectors in the Hilbert space, where I take some orthonormal basis. So this is a state that lives on the tensor product of two copies of my Hilbert space, and these EI vectors here are is some orthonormal basis. Okay. So these are the so-called maximally entangled states. And there's a way in which we can quantify that they're actually maximally entangled, but I will not talk about this. What I need for this overview is the fact that these entangled states have so-called non-local correlation in them, in the sense that if I make local measurements on these entangled quantum states, then for certain measurements the outcomes will be perfectly correlated. Okay, so in this particular case here, if I measure with respect to this orthonormal basis, if you think back to the beginning of the talk, this was just kind of like to figure out what preparation I find my state in, or my system. If I measure these EI states locally on phi plus, gives a stochastic but perfectly correlated outcome. Okay. But perfectly correlated outcomes. And what I mean by this is that if I do this in a product here, and this tensor product here is now what I mean by locally, measuring locally. If I do this on this state, then I get 1 over square root of d exactly when I is equal to j, as you can verify. And so this is now a resource that two parties that each have access to one copy of this bipartite system, what they might be able to use in protocols to their advantage. And the best example of this is so-called teleportation. I have to watch the time. So I have like 5 minutes left, right? Roughly. Yeah, okay. I'll try to get to the point with purpose interpretation. So let me quickly say something about quantum teleportation. What's the idea here? So here we have two parties. Let's call them Alice and Bob, like we usually do. And the idea is that they have some weird entangled state between them. But they're somehow spatially separated. So they only each have access to their local shares of this entangled state, but the entangled state correlates them in a quantum way. Okay, and so now the task for teleportation is that Alice has some additional system that she wants to teleport to Bob using this entanglement. And the way that this can be achieved is that first, Alice performs some measurement on her systems, measure A's systems. And the idea is that what I just said before, if you measure an entangled state locally, then somehow the information of the outcome of that measurement is also available in some way on the other side of that entanglement. However, just the correlation is useless by itself in a sense. But if Alice is now able to tell Bob what outcome she got from that measurement, then Bob can use that information together with the correlation in the entangled state in order to get this state here to the other side. Okay, so the second part of this is that Alice tells Bob about the outcome. And then the third part is that based on this outcome, Bob can apply some kind of so-called recovery or correction operation. And this will, if you do things right, this will teleport the unknown state. Yeah, and I mean, I haven't actually told you how this works because I don't have enough time for this. The idea is just that when Alice performs this measurement in step 1, then she kind of like puts the information of that unknown quantum state into the entangled state. And because of the entanglement, this information is now in principle available at Bob's side as well. So if Alice tells Bob how to kind of like rotate his systems into the right thing, then they can actually achieve teleportation of this unknown quantum state. And so this is kind of like the hand-waving explanation of it. The math is surprisingly simple. So this is something that a student with a background in linear algebra can easily derive if you tell them how to do it. And so this is really amazing how simple but powerful this idea of quantum teleportation is. Okay, and so the catchphrase is always that teleportation is that you use entanglement together with classical information, classical communication in order to implement a so-called quantum channel. Yeah, quantum channel, because this protocol, if you do it in the right way, really allows you to teleport an unknown quantum state from one party to the other one. And so you can think of this as a quantum channel that transports the quantum state or sends the quantum state. Okay, and so now in the last couple of minutes, I want to describe a specific situation of these teleportation protocols, which are called port-based teleportation. So this is now port-based teleportation, which is a specific family of protocols with some nice properties. But the basic setup is the following. So we again have Alice and Bob, which are separated. And now we assume that this entangled state that they share is actually n copies of this maximally entangled state that I wrote down before. Okay, so these wiggly lines usually denote these maximally entangled states. So each of these is a copy of this phi plus state. And we assume that we have n of those. And again, Alice has some additional, and so here each of these systems is some D-level system. Okay, so we assume that they all have the same size for simplicity. And here's another one. And the task is for Alice and Bob to bring this state to Bob using the entanglement and classical communication. Okay, and so now this is a special protocol in the sense that first Alice again does the measurement. Okay, so she performs some measurement on her n+1 systems. And the idea is that this measurement will pick out one of Bob's so-called port systems. So that's where the name port-based comes from. So one of these n systems that Bob has on his side. Okay, so kind of like the measurement has n outcomes, and that label that Alice gets as the measurement outcome just labels Bob's port. So Alice sends outcome, which is a label I in this set of ports to Bob. And then Bob, in the third step, let me write this up here, Bob just picks up the ith port, and this should now hold the teleported state. Okay, so he, for example, if he got the label 2 from Alice, then he would just pick up this and kind of like discard all of these other ports, and then that should somehow have the teleported state. And the idea is now again that if you give me like 2 or 3 more minutes, the idea is here again that you kind of identify the symmetries that you have in this problem. So I think in a way that I wrote it down, I think one thing that's kind of apparent is that the protocol will not actually care about the actual port in which the teleported state lands in the end, right? Because somehow in the entangled state, if you permute both ends with some permutation from the symmetric group, then the whole thing shouldn't care about this. Okay, so the first, let me copy the picture because this will be helpful to look at when I talk about the symmetries. So the first thing is that we again have permutation symmetry. Where this measurement is now a so-called orbit under the symmetric group, meaning that if I apply the permutation to these n states here, I should get like another outcome. So the system, the measurement should be symmetric under this. Okay, it's not invariant now, but it's symmetric in the sense that it forms an orbit under this action. So another way to say this is that we have the symmetric group acting on n of the n+1 systems. So here we have 1 plus these n systems. And the measurement should have this symmetry. Okay. So in comparison to spectrum estimation before, we now have a slightly more complicated symmetry where the permutation group doesn't act on the full n+1 systems, but only on part of them. Okay, but this is not a problem in the analysis. And the other part is again the unitary symmetry. And this comes from the fact that remember the operation that Bob applies in the end, just is kind of like picking up one of these n ports. If you set up the protocol like that, then the protocol doesn't care whether you try to transport, whether you try to teleport a state rho or a unitary rotation of the state rho. Okay, so the protocol works equally well for rho and a rotated version of rho. And if you do the analysis, so here basically you can put now unitaries on each of these ports here. And then when you work this out, you will find that these measurement operators are invariant under the following action. Where we also have something slightly more complicated than before. We again have this diagonal action of the unitary group, but we also have it tensored with a dual representation. So the bar here is complex conjugation. So this again means that as a commutation relation, this means that U bar tensor U tensor N commutes with all of these measurement operators. And this comes actually from the fact that this maximally entangled state has a U tensor U bar symmetry. So this is what you exploit here. Okay. But nevertheless, we have again a situation where we look for a measurement that describes the port-based teleportation protocol, and we can again impose without loss of generality these symmetries on the measurement operators. And then in a similar way as with spectrum estimation before, we can use this to deduce some structure for this measurement. And then it turns out that we can actually write down the measurements that will achieve port-based teleportation in an optimal way for a fixed number of ports. And then we can use that in the analysis of the asymptotics of these teleportation protocols, or to just write down the exact form of these measurements. Unfortunately, I don't really have time for that, and I want to stop here and thank you for your attention. Thanks.
Thank you very much, Felix, for the nice talk. Are there any questions?
So do you have any pointers to look at for the spectrum estimation problem in a little bit more detail?
Yes. So the one very good paper to look at is the following. If you give me a little more time, I can also give you the archive number of this. So this is one where they really describe this in a lot of detail. There's also very nice lecture notes, for example, by Michael Walter on it's lecture notes on quantum information theory, but he has this representation-theoretic focus on them, and he goes through that spectrum estimation in detail as well.
Thank you.
You're welcome. So yeah, I gave some kind of like intro or overview on these. There's obviously a lot more to say about these, but I hope I gave you a taste of these methods and how we use them in quantum information.
Are there other questions?
Yeah, I have a question. So I'm curious, how many copies of the state do you need to get a good approximation to your spectrum? So like, what's the convergence rate look like?
It's actually, you get an exponential error decay. So if you want to be epsilon away from the right spectrum, then if you only want to be epsilon away from the right spectrum, then the error of that will decay exponentially in n. So the convergence is fast.
Oh, that's pretty good.
But it does still take a lot of copies, and if you actually, because we now come to we're now in a time where we start having access to some form of a quantum computer, and you wouldn't want to implement this particular estimation protocol there because it's still very costly. So it might not be the most efficient thing to do when you have only access to a few copies.
Thank you.
Yeah, you're welcome.
So in the port teleportation, you had this phi plus shared between Alice and Bob many times. With other entangled states, could you also do it?
Yes. So this is a very good question. So here, this is a special case of port precipitation where the entangled state has this very nice structure. You can prove that if you take an arbitrary entangled state, then you can always symmetrize it so that you again have these two symmetries here.
I see.
And what the way the proof goes is that you symmetrize the protocol, and then you prove that the new protocol is at least as good as the old one by convexity of the figure of merit that you use. But this is the nice thing about this port precipitation protocol, that these symmetries are somehow built into the protocol, and regardless of the state that you start with, you can always impose them, and this simplifies the discussion of it.
I see.
Yeah.
Thank you. Are there other questions? Well, if there are no other questions, thanks Felix again. Thank you very much, Felix, for the nice talk.
Thanks a lot for having me.
Thank you. I'm gonna stop the recording.
Became a little dark on my end, so I will stop screen sharing.